Hello everybody, welcome back to another video. Today we're going to be solving a very exponential problem. As you can see here, we have x to the power of x to the power of x to the power of x infinitely many times is equal to some number a. Today we're going to be solving for what a really is other than just this definition, and how can we write that in terms of just x instead of this giant infinitely long exponent thing. Alright, let's get right into it. So immediately the first thing we want to realize here when solving this equation is the following. When we write x to the x to the x, we're effectively doing this. Let me write this in one color. X to the, I'll do this in blue. X to the x to the x to the x dot 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 is equal to a, right? And then we have the same thing. X to the x to the x dot 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 equals a. But if you notice, this exponent is really just this. Because we're repeating this infinitely many times, we can replace this exponent with itself, with the entire equation itself. So that allows for a really nice solution. Let me show you what I mean. If we have 2 to the power of 2 to the power of 2, and this is equal to a, we can just write this as, well, this looks pretty obvious, but we can just take this entire thing and put it in the exponent like this, and the colors make it clear. Just like this. Because we're doing it infinitely many times, this does not affect our answer, and this makes it right. So, with this new knowledge now, we can rewrite the original claim of x to the x to the x to the x equals a as this. We can do it like this. Oops. We have x to the power of a is equal to a. And it works out if we try to reverse the process as well. If we say what's a? Well, a is x to the a. So then we get x, and then we replace x to the a equals a. And then what's a again? And then you repeat that process and you'll get x to the x to the x to the x. So now that we have a new form for this equation, how can we solve for a? Well, let's first get x isolated and all the a terms on the right side. So I would raise both sides to the power of 1 over a, like this, 1 over a. So here we get cancel, cancel, and we get x is equal to a to the 1 over a. So now we have a definition for what x is, which is pretty cool if we know what a is. So if we know the answer on the right-hand side, we can calculate x. But I want to calculate a in some other term of this, in some other form than that, because that's you can't compute that. So let's take ln on both sides. If we take the natural log, on the left-hand side, we get natural log of x is equal to, and we bring the exponent down as a coefficient. That's how natural log work. Of ln, so 1 over a times natural log of a. So far, so good. Now let's see what we can do. Still on the left-hand side, we have ln x. On this side, we can describe this as just a to the negative 1, ln a. And that's obvious. So what I'm essentially getting to is we have ln a, this right here, multiplied by e to the ln of a to the minus 1. You can describe any number, let's just call it c, for example. This is always equal to e to the ln, well, not always, because this can't be a negative number. But for the purposes of this solution, let's assume that a is, this is never negative. Otherwise, the natural log will return undefined, or some complex. And I actually did a video on ln of negative numbers, but yeah, let's assume that it's positive for now. So this is under the assumption 1 over a is greater than 0, because ln of 0 is also undefined. So with this new knowledge, we can take a look at what we have here. So all we did is we just rewrote this as a to the negative 1 times ln a. We have ln a right here, and then multiplied by e to the ln of a to the negative 1. And we'll see why we did this in just a sec. These cancel, so it's perfectly equivalent. Now, if you notice, we can bring this exponent down since we have an ln here. So this gives us a natural log of x is equal to natural log of a times e to the negative ln of a. Now, recall, ladies and gentlemen, we have the Lambert W function, one of my favorite functions in all of mathematics. Here's how it's defined. The Lambert W of x times e to the x returns x. That is the definition of the Lambert W function. It is the inverse of this. So essentially, if we have some, as one of my other favorite YouTubers likes to call it, well, we have a fish. We'll just draw out a fish like this. looks like alpha, times e to the fish equals something, we can take the Lambert W on both sides, and this returns us the fish, which is equal to Lambert W of A. It's a pretty handy tool when we're trying to solve these really exponential and crazy functions, all this stuff. So if we notice on the right-hand side of our equation with this new knowledge right here, and I might do a Lambert W video since it's so cool. Let me know if you guys want to see that in the comments down below. On the right-hand side, we have ln A. So this is essentially our fishy. And then right here, we have negative fish though. So can we apply Lambert W yet? Well, no. A requirement for the Lambert W is that the coefficient and the exponent of E are both the same. So how can we bring this negative here? How can we introduce a negative? Simple. We just multiply both sides by -1. We have negative, negative. So this gives us negative natural log of x is equal to negative ln of a times e to the negative ln a. Now we can finally take the Lambert W function just like this. We have Lambert W here, Lambert W here, and then on the left-hand side we get Lambert W of negative ln of x is equal to, what is something times e to the something, return the Lambert W of that. That gives us just that something. That gives us negative ln of a. So now, ladies and gentlemen, all we have to do is just solve for a. Switch the order of everything. So we have negative ln a equals w of negative ln x multiplied by -1. Ln of a equals negative Lambert W of negative ln x. A is equal to e to the we just exponentiate both sides like this. Like that. So a is equal to e to the negative w of negative natural log of x. Just like that. And there we go. That's our answer. We can rewrite, I'll just write this in white because it looks cleaner. Then we have e to the negative w negative natural log of x. And that's the answer of x to the x to the x dot dot dot. What is this even equal to? That's what it's equal to. And we proved it. So the Lambert W, I should, as a quick disclaimer, this is under the assumption that 1 over a is greater than 0, because if not, we can't really do what we did here with the e to the ln. I could do a video explaining cases where this is either, where this is less than 0 and what we do there. Oops. So yeah, I can do a video on that. But that answers the question. What is x to the x to the x dot 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 equal to? It's equal to that. Now, the Lambert W function has multiple branches, and I'll talk about that in a video of the Lambert W function that I do. But essentially, the Lambert W, it looks something like this, and it's not directly a function. This is including all branches of the Lambert W function. It intersects multiple times if you do the horizontal, if you do the vertical line test, meaning it's not a function. But that's why we define multiple branches like this, or W1, W0, all of that. And it's also called the omega function if you've heard of it. In my opinion, the omega looks cooler, so if you want, you can just write it like e to the negative omega. Look how cool that looks. And then negative natural log of x. So yeah, if you have any questions, let me know in the comments down below. Thank you guys for watching. See ya.